Hello everyone. In this lecture, we'll be learning about conditionals in Verilog. The first conditionals that we'll be learning is if-else statement. We have learned about if-else statement in the programming language course that we have done, maybe C or Java or whatever you have learned. So we'll be looking at an example using which we'll be solving we'll be learning about the if-else conditions. So let us take an example of 4 to 1 marks. Here, this is a 4 to 1 marks which have a select pin of S1 and S0 and then input four input pins W0, W1, W2, W3 and an output pin of F. Now if we know from our knowledge of digital electronics F is equal to W0 when S is equal to 0. F is, S is equal to 0 means S0, S1 would be 0, 0. Again F is equal to W1 when S is equal to 1, that is 0, 1. It will be W2 when S is equal to 2, that is 1, 0, and it will be W3 when S is equal to 3, that is 1, 1. That is, F is 0, 0, you will get output as W0, F is 0, 1, W1, F is 0, 1, 0, W2, F is 1, 1, that will get output as W3. So, we'll be using if-else statement in order to make this circuit. So, first thing we do is we create a new project. So from new project wizard, we name it Max 421. We are naming it Max 41. We can name as anything, doesn't matter. Next, 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 finish. And now we open a Verilog APL file. Now the name of our module is Max 41, same as this. And the output of the module is F. Input of the module are W and S. Now it is to be noted that S is 2-bit, W is 4-bit, and F is 1-bit. So we can write as input 3:0 W, that is W is 4-bit, W0, W1, W2, W3. Similarly, input 1:0 S, that is S is 2-bit, S0 is 1, and we have output F. Now it is to be noted that we have learned that in case of Verilog, all the statements that we have are interpreted at the same time. That is, all the lines are executed at the same time. But if we are considering if-else statement, we look at the condition. If this condition is true, we do this thing. Else, we do another set of things. So if the condition is true, we do one set of things. If else, we do another set of things. In this case, if all the lines are executed at the same time, we will not get an anticipated or expected result. So because the lines will not depend on whether the if condition is valid or not. So we have to make an arrangement so that the Verilog code runs line by line. That is, first it executes this line, next this line, next this line. It executes from line to line. In order to do so, we have a function. That function is called always. Always at the rate. Inside that at the rate, we have some variables, and we'll come to these variables later. Just let us look at the codes now. Let us write the codes. If we know if S is equal to 0, then we get F is equal to W naught. Else, if S equal to 1, there are two equals. For conditionals, we have two equals, equal 1. We get F equal to W1. Else, if S equal 2, we get F W0. Since W is an array over here and we are accessing array element, we have to access using third brackets. So F is equal to W2. Else, if none of them are true, else F is equal to W3 and N. Now, one thing is there, if we had put a sign over here, what would have happened? At any time W0 or W1 or W2 or W3 changed, the output would change. But we want to make sure that the output changes based on these logics. If I try to make it more clear, suppose we have W0, W1, W2, W3, and one of those changes. Suppose we have S is equal to 2. So F should be equal to W2. But at that time, since the right side of F there is W0, 1, 2, 3, all of them, if W0 changes, this line of the code will be operational. This particular line will become operational even though the if condition is not fulfilled, and as a result that this F will be equal to W2, which we do not want. So what we need to do? We need to do is we need to make an arrangement so that we can store the value of F without assigning it. So how we can store? We can store it by using output reg. Why do we need reg? Means register or a memory element. Why do we need register? We'll learn about it later. First, let us see that these things will be updated as soon as our switch changes, that is S0, S1 value changes or W changes. With the change of W or S, these output will change. That is, if S moves from S0, if S is equal to 0, if the input changes from S is equal to 0 to S is equal to 2, the output will change from W0 to W2. Again, if S is equal to 2 is fixed, if W2 is changed from 0 to 1, the output will also change from 0 to 1. So, these output, change in these output are dependent on both select pin and W pin. And as soon as either S or W changes, the code will go into the always block and will operate the if, will check the if and else if conditions and will act accordingly. So as soon as S or W, any of one of those updates, the code will go into else if and find the condition which is perfect, and it will set the value of F according to that condition, and it will end module. It will then end the code. Now, by the output rate F, we have used this memory element register because if S and W, none of these change, then what happens? The code never goes into this this if else statement. As a result, what will be the value of F? The value of F at one stage was suppose 1 or W0. Now, if there is no change in S or W, it doesn't go inside the if else conditions, and as a result, new value of F is not assigned. Then how can F retain its old value? It can retain its old value if there is a register or memory element involved. So, in order to state it more easily, we can say that in every case there is an always. In almost most of the case there are exceptions. I'll be telling you about that later. In almost every case there is an always block here, that is we want line by line execution of the code. We will be defining the output as register. Exceptions are there, and I will be telling you about the exceptions in later part when we encounter those exceptions. Now the logic should be operational, so we save this code. We compile this code to check if it works. Okay, the code is working. Now we open a vector waveform file, and then what we do is we insert node or bus. Just select all. Okay. Now what we do is we start from W0. We put a clock, Control Alt K. Say we put a clock of 1 nanosecond. If this is 1 nanosecond, this becomes 2 nanoseconds. This becomes 4 nanoseconds. This becomes 8 nanoseconds. Then which becomes 8 to the 16 nanoseconds, and the last one it becomes control alt K, it becomes 16 to the 32 nanoseconds. So we have used the inputs and outputs. We save this. After save this, we go into assignment settings, functional processing, uh, generate functional simulation at least. Okay, and we simulate the circuit. Now, though this seems a little confusing, we see in in this sorry, in the early this period of time, the input is 0, 0, and we can see the output looks like W0 if you observe it very carefully. Then in next part, this part, the input is 0, 1, and the output looks like W1. In the next part, input is like 1, 0, and output looks like W2. And in the last part, the input is 1, 1, and the output looks like W3. If I zoom it, it will be better visible. Okay. Now it will be a little better visible. So at the initial case, till this point, this is A0, till this point A1, this point, it output is similar to A2, sorry, W2, and at last the output is similar to W3. So our 421 marks is operational and it's working correctly. Now this is done using if-else statement. Now we can do the same thing using case statement. How we can do that? We are deleting the if-else part of the code. We are modifying the same code. We are writing case s colon. Now, if s is equal to 0, f is equal to w0. That is how the case statement works. Case statement checks the value of s bracket. Case statement checks the value of s. If the value of s is 0, then it's making it w0. If the value of s is 1, it's making it W1. If the value of s is 2, it's making it W2. 3, W3. We can modify it, we can change it in another way. We can write 2 prime B 0, 0. That is, since S is a 2-bit binary, we can write it in form of binary as well. 2 prime B 0, 0 means 0. And again, we can write 2 prime B 0, 1. 2 prime B 1, 0. 2 prime B 1, 1. This code and the earlier code means the same. There is no difference in it. So this is the case statement. After the case statement starts, we have to use end case here. So we are doing the same thing. Again we are considering a 421 marks, but in this case, the 421 marks we are considering it or we are building it using the case statement. So we are saving it, and after that I am deleting all the inputs here. Wait, let me first compile this one. There are 4 errors I can see. What are the errors? There were, okay, what's missing? In line number 6, uh, let me check. Okay, there was an error in the statement here. There is no colon over here. Cases, then we write different cases of S and we'll get different outputs. Let us compile the codes and see if it's okay. Okay, simulation is successful now. So we insert node finder. We save it. Here again we modified this as 1. access to four page 16 32. So we are doing this, and again we are saving it. We generate the functional simulation netlist. It's successful and we run the code. Again, if we look at the output, we see at first it follows W0, then when S is 1 it follows W1, when S is 2 it follows W2, and when S is 3 it follows W3. That is, the code is correct, and we can do this using the case statement as well. Now there is a special version of case which is called case X, which might be of our interest. So to explain the case X thing, what we need to do, let us design a 422 encoder. What does encoder do? Suppose the inputs here we have our encoder. We have the 4 inputs W0, W1, W2, W3. What it does is it has 2 outputs, Z0, Z1. If we have 1 here, output is 0, 0 because W0 is active. If we have 1 here, output is 0, 1. If we have 1 here, output is 1, 0. If we have 1 here, output is 1, 1. So in general, the condition for encoder is if one of the input is 1, all the other inputs must be 0. But at some cases it may come that W3 and W1 both W0 both are 1. Then what happens if W3 is 1 and W0 is 1 as well? Then what happens is there is a problem. What's the problem? The problem is it cannot decide whether the output would be 1 1 or the output would be 0 0. So the basic encoder is not really useful, and there are lots of problems. In order to solve these problems, we use a thing called priority encoder. So we suppose determine the priority. Say the priority is in this order. The maximum priority is of W3, then W1, then W0, then W2. That is, if W3 is equal to 1, then Z will be 1 1. If at the same time, if any other input is 1, it doesn't matter, Z will be 1 1. Now if W3 is equal to 0 and W0 is equal to 1, Z would be 0 0. But at the same time, if W1 is equal to 1, then Z will no longer be 0 0. Since the priority of W1 is more, the Z will become 0 1. So the truth table will be something like this: W3, W2, W1, W0, Z1, Z0. The truth table will look like when W3 is 1, it doesn't matter what the other inputs are, Z will be 1 1. Second most priority is W1, and since the priority of W1 is lower than W3, as a result W3 has to be 0 and W1 has to be 1, and the output would be 0 1. So it doesn't matter what are the values in W2, W0. Similarly, if we have 1 here and 0s here, it doesn't matter what we have in W2, output would be 0 0. And the last case, we have 1 here and 0 everywhere else, we will get 1 0. So this is the truth table. Based on this truth table, we will be writing the code of a priority encoder of the priority 3 greater than 1 greater than 2 greater than 0. So we open a new project. We name it ENC for encoder. Next, finish, and we open a Verilog HDL file. Now the code will look like something like this: module ENC. The output is Z. The input is W. Output is Z. Input is W. Now input is, there are 4 inputs. So in port 3:0, W output 1:0 Z. Now the output would be registered because we need line by line operation, line by line execution. So we'll use the block always at the rate. The output changes as soon as the input changes. So always at the inside the always block there will be W. Always with the change of W. Case X W. In case of case, we are writing case X here. We will see why we are writing case X. First condition, uh, first condition is 0 0 condition. So for 0 or any other condition we can do. See, first condition W3 is 1, all the others are 0, then Z is equal to 1 1. So we can write it as 4 prime B. Since the case is W, this has to be 4-bit binary. 1 XXX, that is if W3 is 1, all the other conditions none of the other condition matters, and it will yield an output Z is equal to 2 prime B 1 1. So instead of 2 prime B 1 1, we can actually write 3. Both of them indicate the same. Similarly, if we just copy it and paste it 4 times, second one is W3 will have to be 0 and W1 has to be 1. In that case, we have Z is equal to 1. Third one is W3 has to be 0, W1 has to be 0, W0 has to be 1. Then we have here 0, and here we have 0 1 0 0. Hope this is understandable. This is pretty straightforward code, and we use end case and module. So it is to be noted, whenever we have these don't care conditions, we use case X, or in other cases we use case. We save this. After saving this, we try to compile it and see if all the syntax are okay. It seems they are fine. Now we open the vector waveform file. We insert node. We select all. Okay. Now again, since our inputs are W, we choose this as a random clock set 10 nanosecond. If this is 10 nanosecond, this becomes 20 nanoseconds. This becomes 40 nanoseconds. This becomes 80 nanoseconds. So we save it. After saving it, again we change the settings to functional. We changed it to functional, and then what we do is we generate the functional simulation netlist. It was successful, and we run the code. Now it is to be noted that if we just zoom out a bit, in this time where W3 is equal to 1, we can see output is equal to 3. For this whole amount of time when W3 is equal to 1, we see output is equal to 3. Again, this amount of time when W1 is equal to 1, this amount of time or this amount of time, when W1 is equal to 1 but W3 is 0, in that case output is equal to 1. Then when W0 is equal to, then for the rest of the cases, if we look at it, in this case what happens is W3 is 0, only W0 is active, as a result output is 0. And here all the cases are inactive except W2, as a result output is 2. Here W0 is active and W2 is active, since the priority of 0 is greater and the output is 0. So this acts as a priority encoder. So this is how we can use We can create encoders and marks and all the other logical circuits using if else statement or case statement, and we can include the don't care condition by using case X statement. That's all for now. In the next lecture, we'll be learning about sequential circuits and how we can implement them in Verilog. Thank you.